So I'm going to present our results on the structure of the topmost outer core obtained by the inversion of SKKS and S3KS differential travel times. So unlike the other parts of the Earth, such as the upper mantle, the lower mantle, and even the inner core, the outer core has not been an exciting place for seismological research. And the main reason is because the outer core has been considered to be a well-mixed liquid of mostly iron with some nickel, and also some minor light elements such as oxygen, silicon, and sulfur. And so seismically, the structure of the outer core is very smooth, as shown by these three models. Here are three models, PREM in black, and ISP91 in red, and AK135 in green. And so you can see that the P-wave velocities, they are all very smooth in the whole outer core, except for very narrow zones near the core-mantle boundary and the inner core boundary. And but the geodynamic modelings in the past 2 decades have suggested that the topmost outer core may not be homogeneous but stratified. There are mainly 2 origins for this stratification. One origin is that this stratification was formed during the formation of the outer core. And this stratification has been maintained throughout the geologic time. And the other origin is by the accumulation of its light elements under the core-mantle boundary. And these light elements may come from either from the inner core or from the interaction with the mantle. And also over the past 2 decades, there are also some seismological evidence proposed both for this existence of the stratification and also against the stratification. And all this evidence for the stratification, they are mostly from seismic data along a particular path, a few paths in the Earth, except for this work by Tanaka, and it's using global data set. And this work against this evidence against this stratification is also obtained by a global data set. So in our work, we want to revisit this issue by using a global data set of differential travel times between S3KS and SKKS. And here there are ray paths for these 2 phases at several distances from 120 degrees to 140 degrees. And on the right are the sensitivity kernels of these phases. The top one is the sensitivity of SKKS, and the middle one is S3KS. And this bottom one is the sensitivity of this differential travel time. So you can see that because the Fresnel zones of the SKKS and S3KS, they are very wide. And so the subtraction of these 2 phases in the differential kernel, the pattern is very complicated. And so when you have a global data set, the average property of the data set will not be very sensitive to the structure of the mantle. And so the average result in the global data set will mostly come from the outer core. And here is a profile of the seismograms from 120 degrees to 140 degrees. And these are the seismic records at a number of stations in North America from an earthquake in Sumatra. And because of the long traveling distance, these phases, they are a relatively low long period. And so we have to filter the seismograms down to 0.2 hertz so that we have a higher signal-to-noise ratio. And this makes the reading of the onset times of these phases very difficult. And so in our work, we use the cross-correlation to measure the differential travel times. So we cross-correlate the SKKS with the Hilbert-transformed S3KS. And we do this measurement using both records and also synthetics calculated by the direct solution method. So this shows our path coverage. And finally, we have about 1,500 measurements of this cross-correlation differential travel times. And we use the waveform similarity as standards for quality control. And so in the end, we selected 606 data. And these are from 78 deep earthquakes with a global distribution of the paths. And this top figure shows the 606 measurements, cross-correlation measurements. And we further cleaned the data by removing the measurements beyond one standard deviation. So in the end, we have 489 data to be used for inversion. And first, we did a comparison with the PREM predictions. So we calculated DSM synthetics for PREM and make the cross-correlation measurements. And then we subtract the observed differential travel time and this PREM prediction. So we have this residual relative to PREM. So here, if you see the warm color, that means PREM is too fast. So by looking at this map, we can see immediately that PREM is too fast. And for the inversion, we used the Bayesian inference. It's a statistical approach. So in this approach, we make the inference of the model space based on the a posteriori probability density function, this PPD. And this function is proportional to the a priori probability density and the likelihood. So the likelihood reflects the fitness of the model to the measurements. And this a priori density function is what we know before we make the measurements. So this is the original 489 measurements. And we bin the data by every 0.5 degrees to estimate the uncertainty. That's in the likelihood. And for the a priori probability density distribution, we set the bounds of the model perturbation from PREM. So the lower bound is maximum is 0.2% from PREM, and the upper bound is plus 0.25% from PREM. So these are the two bounds, and the a priori probability density distribution is unity within these two bounds, and is zero outside. And we also, because we want to avoid an artificial discontinuity in the outer core, so we applied a cosine taper so that the perturbation smoothly goes to zero at about 800 kilometers below the core-mantle boundary. And this model is parameterized by 40 depth nodes from the core-mantle boundary down to 800 kilometers below. And this is the result of the inversion. Here we sampled the model space by 40,000 samples. And this red line in the middle is the expectation model. Or it's also the ensemble average of these 40,000 samples. And these two thin lines are the one standard deviation. And these dashed curves are the a priori bounds. So first of all, on average, from the core-mantle boundary down to 800 kilometers below, the expectation model is about 0.07% lower than PREM. And the minimum velocity or the maximum perturbation from PREM is at about 80 kilometers below the core-mantle boundary. And the amplitude is about 0.25% lower than PREM. And we also see this relatively high velocity zone, about 150 kilometers below the core-mantle boundary. And in our model, the perturbation approached to zero at about 550 kilometers below the core-mantle boundary. And we also did some Bootstrap tests. In this test, we used 80% of our whole data set randomly selected. And we used the same inversion approach for the entire data set. And here, the green curves are these are 4 examples of the Bootstrap results. And the green curves are from the Bootstrap inversions, and the red curves are for the entire data set. So you see that all these features remain, and they are very stable, except for some very small features in the model. There are some differences. And also, this is the comparison of our model with 2 recent models. This blue solid curve is the model KHOCQ by Helfrich and Kaneshima 2010. And this dashed blue curve is the model KHOMC by Kaneshima and Helfrich. And you can see that in the top 300 kilometers of the outer core, our models have similar long wavelength features. But our model has a higher degree of undulation, and also the deviation from the PREM model reaches deeper in our model to 550 kilometers, and in their model they reach 300 kilometers below the core-mantle boundary. And so in conclusion, we have used a global data set of SKKS and S3KS differential travel times to obtain a 1D structure, seismic structure for the top of the outer core. And in our differential travel time, our differential travel times are measured by cross-correlation. And in our inversion, we accounted for the finite frequency effect. And in our results, the model is about 0.07% lower, on average lower than PREM. And the lowest velocity is about 80 kilometers below the core-mantle boundary, which is 0.25% lower than PREM. And the undulation with depths of the structure supports the existence of compositional stratification. Thank you very much.
We have some questions.
Just a general comment. The reduction of seismic velocity is not in one-to-one correspondence with the question of stratification. There may be other ways to do it, for example, a two-phase medium. That's just a comment. People seem to assume that it implies stratification, but I don't think you have to make that argument separately from whether you believe the seismic data.
Thank you.
I was just wondering about the parameterization in your model and how that parameterization might affect the results. Have you tried different types of parameterization? What happens?
In this result, we use 40 depth nodes. We also tried 20 depth nodes, and they are basically the same. That's all we tried.
The question at the back.
Have you explored how the strong lateral gradients in D double prime might affect the results? And if you haven't, I have a test to suggest of doing the inversion for half of your data in the strongest lateral gradient zones, either the in or the out, compared to the half of the data that are the weakest lateral gradients to see if you get the same answer.
So far, we have only done this Bootstrap tests. And because we have a global data set, and also by looking at the kernels, the pattern is very, very complicated. And so we think that the mantle effect will contribute to the scattering, in the data, not the average property of the data. So that contributes to the standard deviation, and maybe we can add more data to reduce that standard deviation.
Let's thank the speaker again.